Okay, good afternoon, friends. Last class we discussed open loop system, closed loop systems, the principles of open loop and closed loop control. Then we saw the advantages and limitations of open loop control system and closed loop control systems. And also we saw a generalized block diagram of a feedback control system. And finally, we try to identify various functional elements from a given feedback control system. That's where we had stopped in the last class. Today, briefly, we'll see some concepts of digital closed loop control system, and then we'll proceed for mathematical modeling of mechanical systems. Now, in digital closed loop control system, the systems up till now that we have seen up till now, all were analog control systems. We know the difference between analog control system and digital control system, or analog signal and digital signal. Right. If you see the block diagram of digital closed loop control system, see, you have the reference input and you have the control output. These are same. Correction unit, system or process, and feedback. These are also same. Only thing is that the controller that was there in the earlier feedback control system block was analog controller. Now we have digital controller. Now rest of the signals or rest of the blocks are operating on analog signals. So if I'm going to use a digital controller, I need to first of all convert the analog signal. Let it be a temperature signal, pressure signal, whatever is the physical parameter I'm controlling and I'm sensing. I should convert that analog physical parameter signal or transduced signal into digital value, and then you have a comparator. Of course, this will also be a digital device. So digital comparator, let us say, and then you have the digital controller, and finally, once the control logic is executed, before execution of control logic, this digital output of the digital controller should be converted into appropriate analog signal, and then it should be given to actuating unit, and then process will be controlled. So these three, A to D converter and D to A converters and digital controller and the digital comparator, these will be the additional elements in my digital closed loop control system. If you see, these three are clubbed together and called as microcontroller. Well, we have a separate chapter on microprocessor, microcontroller, and PLC. We'll be studying a bit more details. So all these functions of digital comparison, A to D conversion, D to A conversion, and digital control action are done by a microcontroller, right? And this microcontroller will take care of the signal conditioning work, A to D conversion, D to A conversion, and comparison even. So ultimately, if I remove all the internal elements, how it will appear? So microcontroller will have input pins and output pins. Okay, and reference value will be provided here, and at one more input pin, the measured value or the feedback value will be provided. And from the output pin, analog converted signal will be taken out that will be given to actuating element in the process. This is how my digital closed loop control system functions. Let us move further, friends, and then we'll try to understand why mathematical modeling is required. Now, we already discussed what we do in control system studies is whatever is the physical system, whatever is the physical device, whatever is the physical product that I'm going to develop, design and develop. Now I have to design it for various aspects. When I design a product, I design it from functionality point of view, whatever expected task it is supposed to do, that task it should be able to do. That is called as the functional design. I should work out on the aesthetic part also. If it is a consumer product, I need to think of how it looks and all, isn't it? Whether it is pleasing to the eyes, particularly if I'm using a spectacle, if I'm using a watch, those consumer products, they should have that appeal also. So in that case, I give importance to aesthetic aspects. And if that product is going to be used by human beings, I need to consider some ergonomic aspects as well, isn't it? Ergonomic aspects, that means when the product will be used by the user. Now, if I'm talking about a spectacle, uh, how it will effectively deliver the function it is intended for. Then, how it should rest on my nose, because this will be a generalized design. This angle should be in such a way that it should be able to be accommodated by many people, isn't it? I cannot specifically have a spectacle geometry designed for my needs. Okay, then how I'm going to put it on my ears. So these take care of the ergonomic aspects of this spectacle. Similarly, for each product, suppose I'm talking about a lathe machine. Lathe machine, whatever control wheels I'm using, what should be the diameter of the wheel? So that will decide how much torque I'm going to apply, so that I'll not, the worker will not be fatigued in operating that wheel. So for each product, there will be some ergonomic considerations also. Now, if I'm talking about functional design, when the idea of a product is conceptualized in my mind and I put it on the paper, and then I predict about the functionality of the product under different working conditions, how this product is going to perform. Now, how am I going to predict it unless and until I build that product and subject it to different conditions? Then only I'll be emphatically able to say, yes, it will perform like this under these conditions. The vehicle that is designed uh, on the Himalayan range, where sub-zero temperatures are there, it will work efficiently. How I'm going to authentically say, emphatically say that yes, this vehicle, automobile, will be able to perform in the hot terrain, in the Rajasthan, Kutch area, Gujarat, Kutch area, or hot, sultry climate, hot climate of Rajasthan, uh, for different hilly regions, for cold climate, for peninsular climate, for different climates, this automobile will be able to function. Unless and until I do rigorous experimentation, simulating different working conditions, right? So that is one way of predicting the system performance, and talking about the performance specifications, performance aspects of a product. Now, in this control system approach, we are not going to build any prototype as such. We are going to do, we are going to study the physics of that product, the physical concepts underlying the functioning of that product. Then we'll identify using what physical principles that product or that device is functioning. If I'm talking about a carburetor, let us say, which is a known example for us. Carburetor. What is the functionality? What is the specific task the carburetor does? It receives air, it receives fuel. The carburetor mixes it as per the signal strength I want, whether I want richer air fuel mixture, whether I want leaner air fuel mixture, and it will give the outlet as appropriately mixed or chemically correct air fuel mixture to the engine manifold, inlet manifold, isn't it? That is a function of my carburetor. Now I know the functionality. It receives fresh air, it receives air. Then within the carburetor, I am applying some suction pressure and from the cylinder itself, and because of that suction pressure, this fuel will be atomized and mixed with air, and I'll get air fuel mixture. Now, this is the physical description of the functioning of an of a carburetor. Now, if I'm going to mathematically model this carburetor, now what I'm going to do? At what mass flow rate of air, at what mass flow rate of fuel, at what suction pressure, I'll be getting this much mixture ratio. I want to have air fuel ratio of, let us say, 1:7, let us say, or let us say 7:1. 7 fuel, 7:1. How do I assure that I'll be getting 7:1 fuel air mixture or air fuel mixture? I should design the nozzle in such a way that at this suction pressure, this much will be the airflow rate, and the air having this much density at this airflow rate will provide me this much mass flow rate of the air. And in that, when I'm putting some cc's or some ml of fuel, I have a predefined mass flow rate of fuel. Ultimately, when the mixture comes out, it will have a air fuel ratio of 7:1. On what principle this mixing is based, or this entire functioning of a carburetor is based? I can make use of Bernoulli's equation because it's a flow process. The energy will be conserved. Whatever is going to be the pressure force, whatever is going to be the kinetic energy or pressure energy, kinetic energy, and the potential energy, that will be conserved in this carburetor. So making use of Bernoulli's equation, I'll be able to find out what will be the velocities of flow, what will be the pressures at different points in that flow passage, and what will be ultimately, once I know the velocity of flow, by making use of density of that mixture, I'll be able to predict how much will be the mass flow rate of a mixture. Now, once I know this, that the Bernoulli's equation or the energy equation can be used, I'll be able to prepare a mathematical equation of operation for this carburetor. For these inlet conditions of this much air flow rate and this much fuel flow rate, if I apply this much suction pressure, I'll be getting this much air fuel ratio. So these input-output conditions I can implement, I can supply to this equation of operation, which is based on energy equation, which is based on Bernoulli's concept. And then I'll be able to solve this equation for the output mixture strength. And for different, once I establish an input-output relationship in the form of a equation, maybe in this case, Bernoulli's equation. Once I put different values of air density, air flow rate, fuel density, fuel flow rate, I'll be able to find out how much will be the mass flow rate of the mixture plus what will be the mixture strength or mixture concentration, so to say. So this is one example which would make the concepts of importance of mathematical modeling clear. Remember, I have not yet designed, I have not yet manufactured a carburetor, but what I have done, I have put it on paper. I have put the concept on paper. I have analyzed the physics of this carburetor. I have just established, I have made use of energy equation as the modeling equation. And by making use of this mathematical equation, which describes the dynamics of this carburetor, I'll be able to find out, I'll be able to predict different values of output for different values of input conditions. So likewise, for any physical system, I'll be able to prepare a mathematical model of operation, mathematical equation of operation, and I can subject this mathematical equation of operation to different variety of input conditions, and I'll be able to predict the performance of my given system even on paper, or by making use of a computer, by making use of a software, mathematical modeling software. Or even if I don't have a software, once I know how to solve the equations, differential equations, partial differential equations. By using a simple calculator, by using my knowledge of calculus, I'll be able to solve that equation. I'll be able to predict the performance of my given system. So this is what is briefly the concept of mathematical modeling. In order to understand the behavior of systems, mathematical models are needed. Now, before I build my first prototype, I'm still on the paper. I'm still designing it on the paper. In that case, I need to build a mathematical model. These are simplified representations of certain aspects of a real system. Such a model is created using equations. Such a model is created using equations. These equations are based on physical laws. Depending on the systems involved, if these are mechanical systems, I make use of Newton's laws of motion. If these are electrical systems, I make use of Kirchhoff's laws. In some mechanical systems, I make use of laws of conservation of mass, momentum, and energy, etc. So different physical laws can be used to write the equations of operation. Now these equations are used to describe the relationship between the input and output of a system and can then be used. What way these equations can be used? Can then be used to enable predictions to be made of the behavior of a system under specific conditions. Now, under specific conditions, I'll be thinking about the realistic practical conditions to which this product will be subjected to. If I'm going to design a kitchen mixer, kitchen grinder, let us say. So I should give a thought. What grains will be ground inside that kitchen grinder? Occasionally, with typical Indian mentality, some hard nuts will also be ground. So I need to consider that aspect also. This is additional excessive load factor also we need to consider while designing that grinder. Okay, so those specific conditions, as a designer, I should be able to imagine and think that this product will be subjected to these and these conditions. For example, the outputs of a given set of inputs or the outputs if a particular parameter is changed. Okay, we'll just take the familiar case of a suspension system, which we discussed earlier also. I have designed a suspension system for a two-wheeler. Okay, I have a spring selected. I know how much will be the rider mass and pillion mass. I design the damper. I select appropriate damping ratio, damping factor. I select a spring of appropriate stiffness, and then I have a wheel, and this vehicle will be using this suspension system. Now this I have modeled in the form of mathematical equation of operation. Now under what conditions this suspension system will be subjected? Just try to imagine this vehicle or this two-wheeler. I'll be using it on a plain road, tar road, cement road, sandy road, rough road, village terrain. Under different road conditions, I'll be using this vehicle. I'll be using it on gradients. I'll be using it on slopes. On a bumpy road, I'll be using it. So I need to think and imagine and think to what conditions this suspension system will be subjected to. And corresponding to these different road conditions or working conditions, I'll be able to generate the mathematical equivalent input signals. If the vehicle is moving inside a ditch, so it will be it will be subjected to impulse force. Now, what is the mathematical equivalent of an impulse force? I'll be inputting that mathematical equivalent of an impulse force, and I'll solve that equation of motion of this spring mass dashpot system. And by using this equation, by using this impulse input function, I'll be able to solve that equation to find out how much will be the displacement transmitted to the rider and pillion rider. Isn't it? What for we are using this suspension control system? For comfortable ride. So by using these input conditions, I'll be able to predict how much will be the motion transmitted, how much will be the force transmitted to the rider. And accordingly, I'll modify the stiffness. If the displacement transmitted is more, I'll modify the spring design. I'll change the stiffness value K. I'll change the damping coefficient value of a damper. I'll change the fluid. so that the damping factor will be different. And I'll solve it, solve that equation for different values of K and B, damping factor. And I'll see how much will be the motion transmitted. I'll keep on repeating or iteratively I'll be repeating these values, different values. I'll be changing the input functions also, impulse function, and I'll be continuously doing these iterations till I get the desired minimum displacement transmitted. So this is how I make my design foolproof, and I can predict the performance of my given suspension control system. Now, if my vehicle is moving on a wavy road, right, speed breaker, let us say, so I'll be subjecting this suspension system to sinusoidal input. So what is the mathematical equivalent of sinusoidal function? I'll be inputting that, and I'll just solve that equation for this sinusoidal input, and I'll be able to predict the performance of this suspension system. This is how I can make use of these mathematical models for predicting the system performance. In devising a mathematical model of a system, it is necessary to make assumptions and simplifications, of course, and a balance has to be chosen between simplicity of the model and the need for it to represent the actual real-world behavior. So I cannot have a perfect mathematical model. Some assumptions I need to make, but importance should be given. As we talked about suspension system, my main objective is to improve the comfort of the rider. So motion transmission is sufficient for me. So I'll be identifying what are the major parameters. I ignore some of the minor parameters. I focus on major relevant parameters and I prepare a mathematical model. Otherwise, if I become too realistic and I build a exact model, my equation of operation will become very complicated. It will be difficult. It will be very difficult to solve. I need to make, if it is a non-linear equation, I need to linearize it and then solve it. And it will be very complex methodology of solving that equation. So I have to have a compromise as far as simplicity of equation is concerned. At the same time, the important aspects of the system also should not be ignored. In the process of simplicity, if we ignore the major points, there is no point in building a mathematical model. So this optimum mix of simplifications and realistic involvement is equally important. This is how we are going to study the mathematical modeling, friends. I think we'll stop for today.